Hello viewers, welcome back to my channel Experience of Physics. So this class we are going to see the topic Ohm's law. Ohm's law is the most fundamental law as well as it is most important law of electricity. To analyze electrical circuit, Ohm's law is very important. Let me start from its definition. Definition first. Or statement, at constant temperature the potential difference across the two terminals of the conductor is directly proportional to the current flowing through the conductor. The statement of Ohm's law is at constant temperature. So you have to maintain a constant temperature. The potential difference across the two terminals of the conductor is directly proportional to the current flowing through the conductor. So I will write V is proportional to the current. Let me take one conductor. Yes. I connect a battery of E volts. There flows some current now. The potential difference between the two ends of the conductor is directly proportional to the current flowing through the conductor. So you have written E here. In most of the cases, or we will assume E is approximately equal to V. Strictly speaking, E and V are different, but 99.9% of cases you can approximate E is equal to V, right? So the line drop is neglected. You will come to understand what are them when you go and study Kirchhoff's laws, right? So this case E and V are same. V is directly proportional to I. This is what Ohm's law states. The potential difference between the two ends of the conductor is directly proportional to the current flowing through the conductor, right? So V is proportional to I. Then V is equal to R into I, you know. Resistance of the material. Resistance of the material. This R is further written as rho L by A. R is equal to rho L by A and rho is equal to M upon N E square tau, resistivity of the material, right? So these derivations we have done in a separate video, the origin of resistivity. The origin of resistivity. So in that video we have discussed or we have derived from where R has come, how rho is written as M over N E square tau, right? So you can find the link for this video in the description box, right? If you have not watched that video, you can watch it, right? Let us discuss this R is equal to rho L by A again. So the factors affecting resistance. R is equal to rho L by A. So what are the quantities which are deciding the value of R? rho, resistivity. The material has its value. Material to material it varies, resistivity. Then this is length of the conductor. This is cross-sectional area. So these are the quantities which are deciding the value of R, right? Let me take two conductors. One is longer length, another is shorter length. Its resistance value will be higher, its resistance value will be lower, right? Length is small, area of cross section is more here. Length is larger, cross sectional area is lesser here, right? This is inversely proportional, right? Why? Conceptually, so the free electrons are same. Assume volume, same volume. In the two cases, assume same volume. The free electrons are same. N is equal to same. Free electron density because volume is same, right? So the N, capital N. N is free electron density. N is total number of electrons. They are same because same volume. All the free electrons have to follow a congested path here. So positive ions, immovable positive ions are placed inside the material. They have to collide with the positive ions. Then they have to regain its drift velocity. Then they are moving. So it takes a longer time to cross the two ends. From this end to this end, it takes longer time. T is more here. Whereas here, it is a shorter length and also it is not a congested path. It is not a congested path, right? So all the free electrons which are circulating in the circuit, they can move very fast here. To reach the other end, from this end, they will move very faster, right? So T is equal to small here, right? So T is deciding the current value. Here I is more, I is less. Here I is more in this case. That means R is high here, R is less here, right? So length of the material as well as cross section of the material, they decide the value of resistance. Resistance more, resistance less, right? Rho resistivity, it is material dependent, L and A, right? This is number one. Using this formula, the shape of the material and the material, they are deciding the value of resistance. Number two, we have seen one formula like this. RT is equal to RO of 1 plus alpha delta T. Delta T is a change in temperature. If the room temperature is continuously varying, it will affect the value of temperature. RO is the initial value. RT is the resistance value at one particular temperature. If you change the value of resistance, temperature, it will change, right? This derivation we have done in a separate video. Temperature dependence of resistivity. Temperature dependence of resistivity. This is another video we have done. If you have not watched that video, you can watch it. The link is given in the description box, right? So R is equal to rho L by A, material, length of the material, cross sectional area of the material, and here the temperature. So these are the factors, they are deciding the value of resistance, right? Then let us see the characteristics. VI characteristics of resistance. I take V here, VI characteristic. Since resistance is assumed constant or resistance is constant for a conductor, the curve will be a linear one, right? R is equal to delta V by delta I. Y axis it is delta V. X axis it is delta I. Change in value. This is the initial value, this is a change in value. So R is equal to delta V by delta I. This is known as, we know, slope of the curve. So slope of VI characteristics is resistance. Slope of VI characteristics is resistance. Let me draw the opposite way. Let me take I here and V in this axis, right? Again V is changing, I is changing. V changes, I changes. This is delta I, delta V. Then the slope of this curve is delta I divided by delta V. This will be 1 by R. This 1 by R is known as conductance. So under the heading drift velocity, we have seen conductivity of the material. The reciprocal of conductivity, sigma is equal to 1 by rho. Conductivity, this is resistivity. Similarly, conductance. G is the letter which is used to denote conductance. So G is equal to 1 by R. So this is IV characteristics. If we find the slope of IV characteristics, we will get conductance. Conductance, the property of conductance is to allow the flow of electrons, whereas the property of resistance is to oppose the flow of electrons. Right. Okay, students, let us take few examples. Right. A potential difference of 10 volts is applied across a conductor of resistor 100 ohms. Potential, this is resistance value. Find the number of electrons flowing through the conductor in 5 minutes. In 5 minutes, number of electrons. Number of electrons is asked. V is available, R is available, time is available. So we know I is equal to Q by T, Q is equal to NE by T. Number of electron, charge on the electron, and it is time. I is equal to V by R from Ohm's law. From Ohm's law, we will write I is equal to V by R. So V by R is equal to NE by T. From here, number of electrons N is asked. I will write N is equal to Vt by Re. N is equal to, V is 10 volts, time 5 minutes, make it as seconds, R 100 ohms, and the charge is 1.6 times 10 to the power minus 19. So this is removed. 5 into 6, 30, 10 to the power minus 19 will become 10 to the power plus 19, and this is 1.6. I will write it as 1 by 1.6 into 30 into 10 to the power minus 19. Because this 1 by 1.6 is a popular number, you have to remember it. This value is 0.625. So in chapter 1, you must have used this value frequently. 1 by 1.6 is equal to 0.625. So this is charge on electron. This is the number of electrons required to have 1 coulomb. 0.625. 1 by 1.6 is equal to 0.625 into 30 into 10 to the power of 19. So this is 3 into 0.6, it is 1.8, 3 into 25, 75, 0, 3 into this will be 18, 30 into 0.6, 30 into 0.6 is 18, 3 into 25, 75, into 10 to the power of 90. So this much of electrons are passing. 18.75 into 10 to the power of 18.75 into 10 to the power of 19, option C. So this is 1.8 and also minus 19. Minus 19 should not come. N must be an integer. Minus 19 is the decimal, low, very, very low value. Next. A 6 volts battery is connected to the terminals of a 3 meter long wire of uniform thickness and resistance of 100 ohms. The wire is 3 meter long wire. The difference of potential between 2 points on the wire separated by a distance of 50 centimeter. Actually, the total length is 3 meter. They are asking between 2 points which are separated by 50 centimeter, right? This is 3 meter, right? This is connected by a battery of 6 volts. So there flows some current I amperes, 6 volts. So this is 0 potential and this is 6 voltage. This end plus, so 6 voltage, this is 0. The entire length is 3 meter, but they are asking a distance of voltage separated by a distance of only 50 centimeter. What is the voltage here? Let me write it as V dash. This is V. 6 voltage is equal to V. V is equal to 6 volts. V dash what? So cross-sectional area is uniform. Uniform thickness. Length is only varying. Current is same. Same current is flowing through all the 3 points. Between these 2 points, when 6 voltage is there, right. Between these 2 points, same current, right. So voltage is asked. V is equal to I into R. I into R in turn written as rho L by A. Because L is the variable here. Current same current is flowing, rho same, material, cross-sectional area is also same. So V is proportional to L. Then V dash is proportional to L dash. V by V dash is equal to L by L dash. V is 6 volts, battery value, V. Then V dash is to be found. L is equal to 3 meter, 300 centimeter. This is 50, right? 6 and 6 are also cancelled. V dash is equal to 1 voltage. 1 voltage is the answer. 2 voltage, 1 voltage. Option C. So this can be otherwise solved very easily as this is the entire length. For the entire length, between these 2 points, say this is point A, this is point B. Between point A and point B, 6 voltage is available. Then in between, point C I am taking. Point C. What is the voltage? 6 voltage. This is 50 centimeter, another 50, another 50, 50, 50, 50. 50, 50, 50. The entire length is divided into 6 segments, 6 pieces, right? Then the voltage will also be divided. 1 volts, 1 volts, 1 volts, 1 volts, 1 volts. The answer is 1 volts. So no need of doing. Quickly you can do it, this form. A wire of resistance 4 ohm is used to wind a coil of radius 7 centimeter. The wire has a diameter of 1.4 mm and the specific resistance of its material is 2 into 10 to the power of minus 7 ohm meter. Specific resistance. It is resistivity. The number of turns in the coil. Let me say it is N. Don't confuse it with the free electron density. Number of turns I am assuming it is N. A wire of resistance 4 ohms, R is equal to 4. Coil radius 7 centimeter. The wire has a diameter of 1.4 mm. The specific resistance of the material is 2 times 10 to the power of minus 7 ohm meter. N is what? So we are making a coil using a wire, right? This is one coil. Its radius is 7 centimeter. Radius of the coil. The wire used to wind to form the coil has a diameter 1.4 mm. Wire diameter is 1.4 mm. Its resistivity is also given. This wire gives a ohmic value of resistance value, the entire length. Some turns we are winding. The entire coil, it gives the ohmic value of 4 ohms. Then how many turns they have to be wound? This is the question, right? So we know R is equal to rho L by A. R is available, 4 ohms. Rho is available. L and A are not available directly. A, cross-sectional area of the wire, not the coil, right? Wire diameter is 1.4 mm. So radius 0.7 mm. Then it can be written as 0.7 into 10 to the power of minus 3 meter. Coil radius 7 centimeter. 7 into 10 to the power of minus 2 meter. So for one turn, the length is 2 pi r. We do not know how many turns. In fact, that is the question. How many turns? How many turns they are asking? One turn 2 pi r. If you multiply it with n, you will get the total number of turns. Simple. This is what we are going to do. R is equal to 4 ohms. Rho is equal to 2 into 10 to the power of minus 7. L for 1 turn 2 pi r multiplied by n. 2 pi r is coil radius, 7 into 10 to the power of minus 2 into n, number of turns. So this will give you the total length, 2 pi r into n, total length, rho divided by, now cross sectional area of the wire, pi r square, 0.7 into 10 to the power of minus 3. 0.7 into 10 to the power of minus 3 into 0.7 into r square, right, 10 to the power of minus 3. N has to be found. Pi removed. 10 to the power of minus 3, minus 3, minus 6, this is minus 7. Minus 3, then this will be 10 to the power of minus 1. This is 0.7, this is 7. So this will be 10 times. This 10 to the power of minus 1 and 10 can be removed. Then this 2, 2, 4, they are also removed. Now we are left with n 10 to the power of minus 2 and 0.7. Everything is removed. N is in question. N is equal to 0.7 upon 10 to the power of minus 2, cross multiplying. So this is 0.7 into 10 to the power of 2. This will be 70. 70 is the answer. 50, 60, 40, 70. So the wire is used to wind down coil, some turns, total length calculated, resistance is given, right, that's all. The variation of current and voltage in a conductor is shown in figure. Find the resistance of the conductor, right. VI characteristics, this is linear. So this value will be V divided by I. V divided by I, 9 by 3, 3 ohms. Simple. 3 ohm is answer. The voltage V versus current I graph for a conductor at two different temperatures. V versus I, two different temperatures, T1 and T2 are given. The relationship between T1 and T2 is T1 is higher, both are equal, T1 is lesser than T2, T1 and T2 is equal to 1. What is the relationship? So we know the slope of VI characteristics is R. Slope, so this will be R1, this will be R2. Its slope. Slope will give R1, R2. We know temperature and resistance have direct relationship. RT is equal to RO 1 plus alpha delta T. Direct relationship. So if slope increases, that means R1 increases, that means T1 is higher. If slope is higher, R1 is higher, then T1 is higher, right? So T1 is higher than T2, option A. Resistance and temperature are directly proportional. Limitations of Ohm's law. The Ohm's law is a very powerful law as well as it is very useful law. It has also some limitations. It has some limitations. Let me list them first, then we will have a deep discussion about the limitations. Number 1, V ceases to be proportional to I. V ceases to be proportional to I. That means ceases means stops. Number 2, VI relationship is not same when the battery terminals are reversed. When the battery terminals are reversed, we will not get the same VI relationship. Number 3, VI relationship not unique. These are some of the limitations of Ohm's law. V ceases to be proportional to I, where in ohmic conductors. What are ohmic conductors? The conductors which are obeying Ohm's law. Then this is non-ohmic conductor. This is also non-ohmic conductor. If they do not obey Ohm's law, non-ohmic conductor. Right. Let us discuss them in details. Number one, V ceases to be proportional to I. This is Vi characteristics of one ohmic conductor. Ohmic conductor. We expect a linear line. For ohmic conductors, the relationship between V and I is a linear line, right? So we have also calculated the slope of Vi. Curve is the resistance, constant resistance, right? But this will be deviated after certain amount of current. Up to this point, both the curves are same. So this is one expected curve. This is the actual curve. The green line is the actual curve. Like after certain amount of current, the V stops to be proportional. As long as the current value is up to this point, it is not at all a problem. Up to this point. But after this point, after the value of this current, the VA relationship is deviated from the expected line. Slightly it is deviating, right? So for higher current ranges, this will not be a perfect linear line for higher current ranges. Take for example in the case of heating. In the heating, large amount of current is usually used. For low range current, it is okay. For higher range current, it will be deviating, right? So it is stopped. The relationship is stopped. This is one limitation. This is in the case of ohmic conductors, right? 99% we use ohmic conductors in electrical engineering. In electronics only we are using the semiconductors. Let us take the case number 2 and 3, right? VA relationship is not same. VI relationship is not same when the battery terminals are reversed. This is the VI characteristics of one diode. The device is diode. VI characteristics of diode is one electronic device which is used for rectifier purpose, right? So there is a separate chapter, semiconductor physics, available in class 12 physics. We will study it later. Diode. This is the VI characteristics. So in the first quadrant, look at the shape of the curve. Up to this point, V and I are almost linearly varying. Then after this point, how much V you are increasing, the voltage, the current is kept constant. The current is enormously, it is increasing. Voltage is kept constant. Further increase in voltage does not have any effect on the, for this voltage, the current value is highly increasing. When I reverse the battery, I am coming to negative side, minus V. Then this will be minus I. In this quadrant, up to this point, it is varying, then the current is kept constant. Here the voltage seems to be constant, current is increasing enormously high. Here the current is kept constant. How much voltage you are increasing? Yes, you increase, but the current is kept constant. Also, it is low value of current. In the third quadrant, when you reverse the connections, it is a very, very low value of current. In terms of microamperes, it is milliamperes. See. So this is milliamperes, this is microamperes. Here the current is increasing enormously high. Here the voltage is increasing high and higher, but the current is kept constant. So this is VE characteristics of diode. The materials used are, for the manufacturing of diodes, materials, semiconductors. Say silicon and germanium are popular semiconductor materials. Silicon and germanium, they are used for the manufacturing of diodes, right? So this is the second limitation. When I reverse the terminals of the battery, I am getting minus V, minus I also, but it is not giving the same curve as I got in the first quadrant. Right? Then the third limitation. Again, this is I and V. Look at the shape of the curve. It is linearly increasing, then slightly non-linear, then it is decreasing, then it is increasing. This type of characteristics some devices will possess. The devices are neon lamps, gas discharge tubes. The material gallium arsenide. Gallium arsenide, right? So these are the example of devices which possess this type of characteristics. This is a linear portion. Say up to this point it is linear. Up to this point it is non-linear. Then up to this point it is called as negative resistance region. Then it starts to increase, right? This is linear. V increases, I increases. Here also V increase, I slightly increase. In this portion, V increased, I slightly increased. Here V increased, but I is decreasing. I is decreasing. So it is called as negative resistance region, right? So this type of characteristics, the devices neon lamps and gas discharge tubes will possess. The material is the gallium arsenide. This material is used. Right? If you look at the curve, we will see for the same current, current value is same between these 2 points. Same current, but the voltage value are different. This is V1, this is V2. So different voltage values I am getting for the same current, right? That is why this is also a limitation of Ohm's law, right? So the VA relationship is not unique. This is not unique. The relationship have multiple values. It is not unique. It has multiple values. So this is a third limitation, right? So V ceases to be proportional to I. Expected line, actual line. VA relationship is not same when the battery terminals are reversed, right? In the case of diodes, VA relationship is not unique. Multiple values are there, right? The resistance of a discharge tube, just now we have seen it, non-ohmic conductor. This type of characters it will possess, IV. Discharge neon lamps and discharge tubes, they are non-ohmic conductors. Ohmic 0, both B and C. The VE characteristics of a non-ohmic device is shown. The region representing negative resistance is, yes, V increasing OA. 4 regions are given in the option OA, BC, ABCD. OA, V increases, I increases. Positive resistance. Then AB, yes, almost they are increasing, right? V increases, the increase is very small, but they are increasing. V increases, I increases. The increase may be small, right? V increasing, I decreasing. So B, this is the region where negative resistance is coming, right? BC is the answer. CD again it is increasing. Voltage increases, current increases. Both are increasing, right? Yes. Microscopic form of Ohm's law. Ohm's law, we write it as V is equal to I into R. What is this form? What is the microscopic form? Also it is written as vector form of this topic is also written as topic. Vector form of Ohm's law. This is scalar form of Ohm's law. So vector form or microscopic form we are going to write. V is equal to IR. From electric charges, electric field, electric potential we have studied, V is equal to E into L. Electric field into distance. D instead of distance, we are writing L, length of the conductor. Then I, R rho L by A. L can be removed. This I by A is J. So E is equal to rho J. We know V is a vector. J current density. This is also a vector. Electric field vector rho, it is resistivity of the material. So E is equal to rho J. Also this is written as E is equal to 1 by sigma. Reciprocal of resistivity, conductivity, J. So from here I will take J to the left hand side, sigma E. This is microscopic form of Ohm's law. Or vector form of Ohm's law, vector form of Ohm's law. So this is scalar. Voltage, it's a scalar unit, current is scalar, resistance is scalar. All are vectors here, except sigma. Sigma conductivity of the material. Material to material, it varies, right? So this is microscopic form of Ohm's law. So L and A, they are included here. Length of the conductor and cross-sectional area of the conductor. In E, length of the conductor comes. In J, cross-sectional area of the conductor comes. Current by area, this is V by L. Right, that's all viewers. I hope you have understood what is Ohm's law and the factors affecting resistance value, VI characteristics and limitation of Ohm's law. So different characteristics we have drawn and we have studied the limitation and also we have taken few examples, right? I hope you understood all these things, right? Good luck.